Alright, so here we have a problem. We're saying 3 o'clock, you drive past a sign that says speed checked by drone or by aircraft, and then 7 minutes later, after driving 8 miles, a cop pulls you over. 65 miles an hour was the speed limit. Question is, were you speeding and how do you know? So we saw a bunch of different ways people did this in class. The most common way was to figure out if you drove 8 miles in 7 minutes, what was your average speed? And so to do that, people set up some proportions like this. They said if you went 8 miles in 7 minutes, well, what that was that in miles per hour? So to figure that out, we need to figure out a minute to hour conversion. So there's 60 minutes in 1 hour. And then we can see our units there cross off. So we need 8 times 60 divided by 7 is 68.571, and those units are now miles per hour. So that represents the average speed. So yes, you were speeding. If your average speed is 68.571, you had to have been going at least 68.571 at some point in time. So yeah, you sped and you can get a ticket. Another way people figured this out was they said, all right, well, what if you drove the speed limit, 65 miles in 1 hour? What if you drove that speed limit for 7 minutes? So then they had to do times 7. And what you can do is you can actually just say 60 minutes down there, 65 miles in 60 minutes times 7 minutes. Then we can see our units are going to cancel. So 65 divided by 60 times 7, and you get 7.583 repeating miles, which represents the distance you should have covered if you were going exactly the speed limit. And we went farther than that, so again, we had to have sped somewhere in there. So yeah, we're getting a ticket. So in this lesson, we looked at a bunch of different position versus time functions. So I was standing over here at a whiteboard, and I was walking down the whiteboard, and you had to say if this was 0 and this was 1, 2, 3, 4, 5, 6, 7, 8, 9. I stood and I counted out numbers representing the seconds, and you had to graph my position with respect to time. And on the first one, I just stood directly underneath the number 3, and that, of course, is going to be a constant position with respect to time. I did not move. So as time in seconds marched on, my position in feet, how do I want to say that? Yeah, that's how I want to say it. My position in feet stayed the same at 3, so I got the boring constant function, which was a horizontal line. The next situation was a little more interesting. This time I started at 8 and I walked this direction and ended at 0 after 8 seconds. So this time my position with respect to feet, my position in feet with respect to time in seconds started up at 8 and ended at a position of 0 when the time equaled 8. So this time I got a linear function going down like that. So this time I started at position 2, and then after 1 second moved to position 4, and after 2 seconds moved to position 6, and after 3 seconds moved to position 8. So I ended up with that linear function with a y-intercept of 2 and a slope of 2. And then I started at 0, and then after 1 second moved to 1, after 2 seconds moved to 4, and after 3 seconds moved to 9. So maybe you can see that I am getting this quadratic situation here going up like that. And then finally, I threw a ball in the air. So the position in feet starting on the ground, time in seconds starting at 0. Threw the ball straight up, and you were telling me what is the height of the ball with respect to time. Well, if you think about it, it's going to go up, it's going to go up, it's going to start slowing down. It's eventually going to reach its highest point, and then it's going to start coming down again with that same speed. So you're going to get a nice, pretty parabola just like that. Then the last situation, there was a video I showed of me bungee jumping, going down, and then bouncing back up and down like that, and then eventually being pulled back up. And you're supposed to graph again that position function, position in feet. Actually, this one was in meters, and the time in. Well, honestly, we don't need to put the units there. We just know it's position and time. But the idea is I started at the top and I kind of dove out, so I got maybe upwards a little bit, but then I went down and then I hit the maximum, and or the end of the rope, and so then I turned and went back up, and then I kind of oscillated back and forth as I went to equilibrium, and then they hauled me back up at a constant rate. So a little linear bit right there. And now what we want to do is we want to go through and take the derivative of each function, sketch the derivative, and we want to think about what the units represent when we do so. Well, since this is a horizontal line, I'm just going to get a derivative at y equals 0. So there's f prime. This one, my slope was -1 of this function, so this time I get a horizontal line at -1. Still not super exciting. Here I had a slope of 2, so now I have again a horizontal line, but this time at 2. And finally it gets interesting when I have the quadratic one here. Well, this function, f of x, was x squared. So my derivative of that needs to be the function y equals 2x. Now the reason this is interesting is because this is no longer a horizontal line. So let's think of the units here. Here I have feet in seconds, and this derivative function, f prime of x, is representing the slope of this function at each tangent line slope. So think about what the slope represents. The slope is rise over run, y over x. So think about those units. That's feet over seconds. So my y values here represent feet per second. Feet per second is a speed, like miles per hour. So we took the derivative of a position function and we got a velocity function. If we now took the derivative again of the velocity function, take the derivative, take the slope of this line, we know it's y equals 2x, so now the acceleration, or I'm sorry, I ruined it. Now this is going to be a horizontal line there with the y value of 2. But again, think of the units. Now we have seconds on the x-axis of our velocity function, seconds here as well, that's going to stay the same, but now the y values represent the slope of the velocity function. And so we have, again, you got to think of it as y over x. Well, my y is now feet per second over my x is seconds. So this is feet per second squared. This is your acceleration function. Huge idea. Have a position function, take the derivative, get a velocity function. Have a velocity function, take the derivative, get an acceleration function. So let's go through and sketch these derivatives real quick just for fun. So if I sketch the velocity function, notice that that is a negative parabola, a parabola with a coefficient of some negative number. So we're going to remember our technique for sketching these derivatives. If you go down, I know I'm going to have a 0 at that middle point there where the tangent line would be horizontal and have a slope of 0. So I know then over here I'm going to have a 0 there. To the left of this, my function's increasing. To the right, my function's decreasing. So I need to look something like that. And then if we were to take the acceleration function of this, we would end up with some sort of negative horizontal line like that. And then the most interesting one to take the derivative of. So in doing this, the first thing I would do was I would go through and I would mark all of my zeros by finding the mins and maxes like that. And this is obviously just a rough sketch, so we're doing our best here. But a bunch of mins and zeros there. And then figure out where it's increasing, decreasing, increasing, decreasing, increasing, decreasing, etc. It's going to oscillate. So I know it's going to look something like this, squiggling down like that. But then I hit this point right here where I have a constant slope, so that's going to be taking me up with some constant slope going over horizontal like that.